Okay, guys, let's continue with sections 10.9. And we're going to do a few examples. Two should be good. Okay, in the first example, computer flux. Of F equal, this is the vector field F here. X, E, Y, Z minus E, Y, Z through the ellipsoid. Okay, here comes the ellipsoid. X squared plus 2y squared plus 3z squared equal 4. It is not a sphere, so you can do this one directly, but it's gonna be crazy though. Well, this is an ellipsoid, so very similar to a spherical. Here's how you parameterize sphere. A sphere is the, well, x squared plus y squared plus z squared equal r squared, right? Most of, I mean, hopefully everybody, not most though. X equal to r psi phi cosine theta, y equal r psi phi psi theta, z equal r cosine phi. So when you parameterize the sphere, you get this one. However, if you parameterize the I got to get the limit here. Phi go from 0 to pi, theta from 0 to 2 pi. Parameterized ellipsoid. X squared over a squared plus y squared over b squared plus c squared over z squared equal 1. So when you parameterize it, instead of r, you're going to have ABC. B psi phi psi theta, z equals c cosine phi, and then, well, ellipsoid, the angle phi is the same, 0 to pi. The angle theta is 0 to pi. It is possible to do the parameterization, but when you do the substitution and when you compute f dot ds, oh man, that is crazy, man. We don't have to deal with the parameterization of s. That is the cool hint about the divergence theorem, is that the flux is the triple integral over the solid E enclosed by the surface S. DIVF, divergent F, dV. Very powerful theorem. Divergent F is the partial derivative with respect to x up, first component, x, e, y. Partial derivative with respect to y, second component, z minus ey. Partial derivative with respect to z, last component, z. And then dv. Right. So what do we have here? We have a EY minus EY plus 1 dV, and it is just 1 dV. So what is this one? This is just the volume of the E. Yeah. And hopefully most of you know how to compute the volume of an ellipsoid, right? It should be very similar to a volume of a sphere. Huh? Volume of the ellipsoid is 4/3 pi instead of r to the power 3, right? You have ABC. And then we just have to figure out the ABC here. Look at the ellipsoid here. Ellipsoid is the x squared plus 2y squared plus 3z squared equal 4. So we can figure out the ABC here. X squared plus 2y squared plus 3z squared equal 4. So I mean x squared over 4 plus 2y squared over 4 plus 3z squared over 4 equal 1. And then from here, you guys can get the ABC. No. X squared over 2 squared plus y squared over, okay, so it's 2, right? It's going to be root 2 squared. And then 3 over 4. You flip it, it's going to be z squared. Well, you want to put square here, so it's going to be 2 over root 3 square. So we have the ABC here. Okay. 4/3 pi. I'll put a parenthesis right here so you can see ABC a little clearer. Root 2 and 2 over root 3. So what do we have? We have a 10 root 2 pi over 3 root 3, because there was one on the surface integral that it's the perfect example. God, look at this thing here. And then I told you this thing here. Let's just do this thing here. Perfect example of how the divergence theorem is very useful. Okay, so we have this one. Ta-da! Last time, if you look at it, if you do directly, let's see, look at here. This is the flux there. Yeah, you got to go through 3 different surface integral. Oh, that can be pretty, long and tedious. We can use the divergence theorem because the S1, S2, S3, they enclose a solid. S f dot ds that is equal to triple integral E divf dE. It's a good review too on how to compute a volume of a solid here. I mean, not dE, those dV. Okay, triple integral E, and then divf here is the partial with respect to x. What's the vector field here? xy plus 2xz partial with respect to y, x squared plus y squared. Partial with respect to z, xy minus z squared dv. Okay. What do we have here? Taking the partial derivative with respect to x, we get y plus 2z. With respect to y plus 2y. And then with respect to z minus 2z dv. Okay, so triple integral e 3y dv. So what we are computing here is that we turn the flux into mass of a solid with a density function. Let's say pop the cylinder, so we're going to be using a cylindrical coordinate. Okay, so cylindrical coordinate is the dv is gonna be, oh actually let's do a little review here. It's z dA, and then the dA here is RD theta, because you can parameterize this dA using a polar coordinate. So the dv actually is the z or d theta. Okay, we're gonna need to know where does the limit here, r and theta and z. So where does the z go from? Z, the radius r, the angle theta, cylindrical coordinate. Might as well copy the picture down here. Yes, I think I can copy and scale this thing down here so you can see a little bit more clearly. Oh my God, no. Delete. No. I thought I can copy that one, but no. Oh, no. Okay. Look at the picture here. You guys can see that z go from y minus 2 to 0. However, you got to turn the dA into RD theta. So what is y here? In polar coordinate, y is r sine theta. So r sine theta minus 2 less than equal z less than equal to 0. And then the radius here is, well, you push everything onto the xy plane, you see that radius is 0 to 2, and then the angle is, it's the full circle, so the angle is everywhere. 0 to 2 pi. So if you use rectangular coordinate dz, dy, dx, just I want to project the solid onto the xy plane, and this is the projection of okay. Next step is the z. The z, well, z is pretty straightforward. It go from y minus 2 to 0. What about the y? You see, x and y is when you push it onto the xy plane, you get a disk of radius 2, right? So y gonna go from negative root of 4 minus x squared to root of 4 minus x squared, and then x go from negative 2 to 2, right? So that means your triple integral here is gonna be a little ugly though. Three y dv negative 2 to 2, negative 4 minus x squared, 4 minus x squared, right? Y minus 2 to 0, 2y dz dy dx, terrible to integrate using cylindrical coordinate. Life is a little easier. Reason why, because you're gonna be doing this instead. 0 to 2 pi, 0 to 2, right? Or sine theta minus 2 to 0, and then in here 3y is going to be 3. The y is all sine theta. dv is z or d theta. Okay, so here's going to be a 3r squared sine theta, and then z squared over 2 oh my god, r sine theta minus 2 to 0 dr d theta. Okay, plug it in here. Then you just have to be a little careful with this thing here. 0 to 2 pi, 0 to 2, r squared sine theta, 0 minus r squared sine theta minus 2 squared, r sine theta minus 2 squared, d or d theta, but the dz here. It should be dz here. dz or d or d theta. Yeah. dz or d theta. Oh, so you, oh man, I forgot that dz here. So there's just z here. Oh, make my life easy. So it's going to be this one. 3 minus minus going to be a plus, right? So I'm going to sit or square sine theta minus 3 r to the 3 sine square theta. D or d theta. Okay, and work it out. This with respect to the radius is not too bad. Yeah. Okay, so r3 over 3 is gonna be 2 or 3 sine theta minus 3 over 4 or 4 sine square theta. 0 to 2 d theta. Okay, work it out. So plug in the 2 in here. We get a 10 sine theta. Okay, plug in the 2 in here. So minus 2 to the 4 is 16, right? So 16 divided by 4 is 6, so minus 12 sine square theta. And then when you plug in 0, you're just going to get a 0. Okay. Now you just have to integrate this thing. Oh man, you have a sine square here, so I'm just gonna rewrite this as 10 sine theta and then minus 12. Sine square is half of 1 minus cosine 2 theta. Okay. Next gonna be a integral of sine negative cosine, so it's going to be negative 16 cosine theta minus 6 integral of 1 is theta. And then integral of cosine is sine, so but then you have to divide by 2, so it's negative 1 over 2 sine 2 theta. 0 to 2 pi. Okay. Woo. See what do we have here? We have a cosine of 2 pi is 1, right? So negative 16 times 1. I just do the direct substitution in here, so it's not going to be like last time. Right? Minus 6 times 2 pi minus 1 over 2. Okay, sine of any multiple pi is going to be 0. Okay, so get this thing here, and then going to be 0. So cosine of 0 is 1, so negative 16 times 1. Minus 6 times 0. Okay. Woo. What do we have here? We have a negative 16 minus 12 pi. Minus 12 pi here. Plus 16. So in the end, the answer is 9 minus 12 pi.